So Julian's from Juniper. Welcome. Is
Thank
this
you.
your first time speaking here?
No, I've been a few times, maybe
Okay.
3 or 4 times
Okay,
over
so
time.
welcome back.
Thank you very much.
I will hand you over to the audience.
Great, thank
Be
you.
nice to him.
Great. Hi, everyone. Yes, great to be back here again for the 15th edition. Today I'm going to talk about black hole detection in packet networks. Really, looking for black holes in the network can be traditionally quite problematic. The worst case is if it's your end customers who are the first to notice it, and then operations are, scrambling to try to work out where the black hole is. Even working out which PE the black hole is occurring on can be difficult in itself. And then when you identify which PE, knowing what the actual nature of the black hole is and what types of packets are being affected is the next stage of investigation, which can also be quite time-consuming. And so really it is like looking for a needle in a haystack. And transient drops are also particularly difficult to detect. You might get some issues with some transient black holing, and by the time you get to investigate, all the sort of evidence has gone. Perhaps the black hole's gone away, but you still want to know what actually happened during that time, of course. So what I want to talk about today is 2 main approaches to detecting these black holes. First of all, I'll say some words about indirect detection. But in fact, the main purpose of the talk is to talk about a new method for direct detection. So that would be the main theme of today. So first of all, indirect detection. So what you can do is you can send some probes through the network in different directions following different paths. And you can see in this diagram, we're sending 6 different probes. And of those, most of them are getting through, but you can see that probe number 5 and probe number 3 are actually getting lost somewhere in the network. And so what one does with indirect detection is to do some triangulation. And so knowing the topology of the network and the way the probes are traveling through the network, you can see that both probe 5 and probe 3, which were the ones that were lost, have got R1 in common and only R1 in common. And so it's reasonable to assume that probably R1 is the culprit, and you start investigating R1 a bit further. And so that's the sort of triangulation method that's used for indirect detection. But there is an issue with indirect detection. The main one is that a black hole might only affect packets with particular characteristics, particular destination address, particular label, particular packet size, etc. And the probe packets might not have those characteristics. So those are getting through perfectly fine, but particular packets are still being black holed. And also, as the network gets bigger and bigger, triangulation becomes increasingly difficult, because you'll get probes being dropped for random reasons, like a link going down, you'll lose a couple of probes, and multiple things happening in different parts of the network at the same time. So if we go back to our example, here this time you can see that probe 2, probe 3, probe 4, and probe 5 are not making it through. And what's causing that? It could be a combination of R3 and R1 black holing, or R2 and R4 black holing, or other combinations of those. And so as the network gets bigger, doing this type of triangulation gets more and more complex. And also knowing what particular path a probe might be following isn't necessarily easy either. And so what I want to do is to turn our attention to direct detection. And so the key principle behind that is, packets don't get dropped just for fun. A router knows why it's dropping a packet. And so what this method uses is the fact that the router dropping the packet proactively sends a report about it to an external collector. And that's what we call an exception report. It was an exception packet. The packet was dropped, so that means it's an exception packet. And the key thing is the report, as you'll see shortly, contains a reason code, the actual reason why the packet was dropped, plus a lot of extra metadata. And the scheme is generic in the sense that it works with any kind of packet that the router can forward. It could be IP version 4 or IP version 6 or MPLS or layer 2. It doesn't matter what sort of packet it is. So let's have a little look in a bit more detail. And so that grey rectangle in the middle of the slide, that is one router. And it has multiple packet forwarding engines, or perhaps just one packet forwarding engine if it's a pizza box. And that's the thing that's doing the packet processing. So it's doing lookup on the packet header, analyzing that, working out which way to send the packet, doing other processing. And normally it just send it out on the egress interface. But in this situation, if the packet forwarding engine needs to drop the packet for some reason, what it does is to send this exception report to an external collector, and it actually uses IPFIX. IPFIX is a good choice because routers nowadays, the packet forwarding engines, the ASICs, are able to do IPFIX inline for just normal flow analysis, and so we can leverage that and use it for this exception reporting as well, because all the machinery is there to be able to construct these IPFIX packets and emit them directly from the PFE to an external collector. The other thing you can do, especially for lab work, is if you want to avoid having to go to the trouble of setting up an external collector, if you're just having a quick go with this functionality, is you can just send it upstairs on the router to the control plane, the routing engine, and have a local collector put it into an SQLite database or into log files. That makes it easier to do lab tests. In terms of Juniper, we were the inventors of this, and it's called Juniper Resiliency Interface. If you're looking at our tech pubs, it's been available for about 3 or 4 years now. It's been very successful, so quite a lot of production networks have deployed it, and the people who deployed it found it a very useful tool, making it much easier to detect these black holes. Now, when I say black hole, sometimes people use the word black hole to imply that the router's misbehaving. It dropped the packet and it shouldn't have. But of course, there are legitimate reasons for a router to drop a packet as well. And so I'm using black hole in this more wider context. And so that's what this scheme does. It deals with whatever reason the router, or in particular the packet forwarding engine, needed to drop the packet. That's recorded in these IPFIX-based exception reports that get sent out. So what are some reasons or categories why the packet could be dropped? And these each have a corresponding exception code, of course, in the IPFIX packet. And these are just examples. There are several dozen of these in practice, of these reason codes. And so first of all, unknown address family. So suppose you're running an MPLS network. Normally, you just run MPLS within your network. You don't allow MPLS packets to come in from outside. By default, MPLS is fail closed. It's not on by default on an interface. So if somebody's trying to probe your network, perhaps they're maliciously trying to send MPLS packets into your network, they're going to get dropped by your externally facing interfaces. But you might want to know that they're trying to do this, and so that will actually generate a corresponding exception report sent out via IPFIX. No matching IP prefix in the fib. The packet comes in with destination w.x.y.z. That simply doesn't exist in the fib, and so it must be dropped, and you'll get an exception report. Similarly, for MPLS labels, packet comes in with MPLS label A, and that's simply not there in the fib. Perhaps the fib's been misprogrammed, and so the packet is dropped. I mean, in the early days of segment routing, one of the reasons why people might have seen this is that they used to configure label stacks manually on the ingress router. They used to say, push label 137, 48, 28, 9, 42 or something. And when the packet comes with topmost label 42 at a transit router, if it doesn't know what 42 means, because somebody mistyped 42 on that ingress router, it would have needed to be dropped. And so this would detect that. TTL expired could be due to transient micro loops or permanent loops if somebody's got, static routes pointing at each other incorrectly. Some layer 2 things, unknown VLAN tags. So a packet arrives at an interface with VLAN tag 101, and that's simply not been configured on that interface. And then some things, if you're doing bridging or EVPN, MAC learn limit exceeded. So you've actually blown the MAC limit that's been configured, and so those offending packets will be dropped, of course. MTU exceeded, so if your network supports jumbo frames, you're supposed to set your MTU accordingly on all your links. Perhaps somebody forgot to do that on some link in the middle of the network, and so of course it's only the bigger packets that are going to be dropped, and so spotting that can be quite tricky in a big network. And then the bottom row of this slide, various malformed packets like header errors and checksum errors and the declared length not matching the actual length of the packet is received. So those are the types of categories, examples of those. Each of those has a corresponding exception code in the IPFIX report that gets sent out when the PFE drops the packet. So if you want to do some tests in the lab, this is the easiest way of setting up some tests. You could just have 3 routers in a row. R2 in the middle is the device under test. In this diagram, what we're doing is we're pinging the router on the right-hand side, R3, from R1, but we're setting the TTL to 1 deliberately, and so that's going to be dropped on R2, and that's going to cause it to send one of these exception reports. Or you could do the MTU thing that I mentioned. You could have a larger MTU between R1 and R2 than between R2 and R3, and then send packets with a size somewhere in between those 2 MTUs, and then it's going to get dropped by R2 and generate an exception report. Or another quite easy one to do is just have a static route on R1 pointing towards R2 or beyond. But R2 simply hasn't got that prefix in its fib, so it will send an exception report because there's no matching prefix in the fib. So those are quite easy ones to actually set up in the lab. And then what you can do is, you could set up an external collector, or if you just want to have a quick look in the lab, you can just send it to the local routing engine on the router where it will put it into a file. And here's an example of that. And so what I'll do is I'll step through the different information elements in this IPFIX exception report. And so first of all, you can see highlighted in yellow the exception codes. That was the reason this particular packet had been dropped. And the value has been translated into human readable text in the actual physical IPFIX packet. It's a numerical code, of course. And so you can see TTL expired highlighted there in yellow. But we can look at some of these other fields as well. NH index, that's the next hop index, value 707. And so that's an index into the forwarding structure that describes how that packet would have been forwarded. In this particular example, as it happened in this network, it was running LDP, and 707 would have been saying, oh, if the label packet comes in with label Y, then pop the label and send it out on interface GIGI 100 towards the egress node, which was R3 in that diagram. So that's effectively telling you useful metadata about the actual forwarding entry that would have been used to send that packet if it exists. OIF index, that's the outbound interface index, if that had been determined at the point the packet had been dropped. Here it's 0 because TTL had expired, so there's no point even determining the outbound interface index at that point. The header processing would have stopped at that point. And then if we look on the right-hand side, you've got second one down, the incoming interface index, the index of the interface on which the packet had arrived. But also, very useful if the packet's arriving on a lag, we've got multiple member links, which particular member link the packet had arrived on, because that might be pointing to something. Maybe it's something to do with a particular member link that's causing particular packets to be dropped. That's the one on the top of the right-hand column. And then you've got flow direction. So that's set to 0 if it was the ingress packet forwarding engine that dropped the packet, or it'd be set to 0, 1 if it was the outbound packet forwarding engine. And then the first few bytes of the packet, in this example, the first 64 bytes of the packet, extra metadata. So all of this combined is actually very useful information telling you about the nature of this black hole, why packets are being dropped by this particular router. Now, it's useful to standardize these things, and so we are co-authors on this draft cited here, which first of all proposes new IPFIX information elements needed for reporting these exceptions, because you'll probably have recognized that some of those information elements that you saw in the previous capture don't exist in pre-existing IPFIX. It proposes the new ones needed to support this. And then also it proposes putting the reason codes in an IANA registry, because you want these codes to be set in stone, standardized, etc., to allow for interrupts. That's what that draft is all about. And so if we go back to the previous capture that we did, you can see which are the required new IPFIX information elements. So the ones in green. So the exception code itself, that's a new IPFIX information element. That next hop index that I discussed. The underlying interface index, I mean, that's sort of generic use apart from, this particular application, and also the flow direction, which packet forwarding engine had dropped the packet. So that brings me almost to the end. So I've talked mostly about what's happening, on the actual router, but then, the external collector. The external collector is important to be able to do some analytics on the packet. You could, build your own, perhaps on the basis of, IPFIX tooling that's available out there. We have a platform called Paragon Automation where we're introducing the collection part. And so the thing is, the automation platform is ingesting these IPFIX exception reports, but also other information like through streaming telemetry, interface statistics, protocol errors, things like that. BGPLS for topological information. BMP ingests for allowing the routers to stream the contents of their BGP, adjacency rib in, adjacency rib out, and local rib. And so therefore the collector, on the collector side, it's performing filtering and analytics, correlating the IPFIX exception reports with other events that it's observing happening on the network. The AI word, here it is popping up again in this talk, doing root cause analysis with the aid of AI, and raising alarms and alerts, and leading to remediation. So the external collector part is also important to complement what the router's doing in actually sending the exception reports in the first place. So this is the final slide. If you're interested in reading more, there's some links to our tech pubs and also these blogs which dig into a lot more details about all of this. So with that, thank you very much.
Do we have any questions? Because we have lots of time for questions. No questions? Oh, we have a question. And I promise we didn't bribe him.
Hi, Mikkel from GitHub. Does this need some kind of like more fancy forwarding hardware, or would it also work with like Broadcom chips and stuff?
Oh, it's an interesting question. I mean, we haven't implemented it on any Broadcom platforms yet. I mean, certainly, we've done it on ours. So the things we've done it on is our MX and our PTX systems, which use our own in-house, silicon. So, I guess if this picks up, then, other chip sources would probably want to, implement the infrastructure to achieve it over the course of time.
Thank you.
Hi, Aleksi Suonen from Finland. I think your slides mentioned the year that this support was implemented, but what Juno's version do I need if I want to try it out?
Right. That'll be in the first link on that on the ultimate slide, actually. So that's, lays out, platform hardware versus different releases. But, some of the things were out in, 22 something, actually. No, 21 something, actually, in the first instance. Yeah. So depending on, which router, some of it's been around for, I guess, 3.5 years or so.
I collect IPFIX from Juniper using NF-CAPD. Do I need something else to collect this type of data, or how do I?
I mean, they are IPFIX packets, so as long as it understands the different fields in it, that's fine. So things like, you don't have to use. What I'm saying is, you don't have to use our collector. Like things like, GoFlow2 or PMACT, could be used for it. You need to define, do a bit of customization to define the extra fields, corresponding to the information elements that are new, but you can do it. And in fact, in one of the blogs, it discusses doing that. So the second of the two blogs on that list, discusses that. In fact.
Thanks.
I'm Anton, and
could you get a bit closer to the microphone, please?
Yeah, it's also IPFIX related question.
And who are you?
I'm Anton from FIBE. Normally, IPFIX has those sampling policies and stuff, so that if there's too much, then it doesn't send out too much. Are those policies also applied to the exceptions as well?
Yes. So you can have a separate instance, in terms of the definitions to the regular IPFIX. So let's say the router's streaming out regular IPFIX, just for flow analysis and also doing these exception reports. You can, configure them separately. So you could have different sampling rates and, things like that. I mean, from the router point of view, given that, modern routers on the packet forwarding engine, they can stream out, pretty good sampling rates, the regular flows. Presumably these exception reports are at a lower, occurring less frequently than real packets coming in, or, packets that do get successfully forwarded. So, potentially you could afford to have a more rapid sampling rate on the exception packets than on the normal flow packets. And therefore you've got the degrees of freedom to, set them, at different sampling rates if you wish.
Yeah. Thank you.
Okay. Thank you very much, Julian, and
thank you very
welcome
much.
back.
Oh, thank you.